So I'll give you some things here to think about from a spectrum standpoint, and then I'll see if I can answer any questions. But first of all, I'll talk a little bit about what is spectrum, why it's important to NASA, why it's important really to all of us. I'll talk to you a little bit about the key players. I'll talk to you about the spectrum management process, which has been amazing for me to see how all that works, and I'll explain that to you a little bit in a top level thing. And then I'll talk to you about where we are with the future and what's happening with spectrum and how it's really becoming a constrained resource that is really becoming a high value commodity for lots of folks to go use. So first of all, what is spectrum? It's the electromagnetic spectrum describes the entire range of radiated energy from low frequency radio waves on the left down there all the way up to cosmic rays on the right. So you can see the huge spectrum. It includes optical as well in there between IR and UV. I'll talk to you predominantly about the radio frequency spectrum. That's where most of our communication satellites occur. That's where your Blackberries work, your cell phones, your iPads, iPhones, all those. And we'll talk to you about a lot of competition in that region. And then also we're starting to get into the optical region where we're starting to use laser communications for lots of activities, especially on some of our spacecraft. But that's a new emerging way to transfer lots of information in the optical spectrum. Why is this important to NASA? And I would say every mission that we fly requires some way to communicate with the satellite. If you can't get the data back, you can't get the pictures back, nothing happens. And I often amuse some of my program project managers. They think their satellites, their programs are the most important part. The real unsung heroes of all our missions are the communications people that sit in the background. The ones and zeros that come down and make the images from Mars, the fantastic pictures I use. None of those would be possible without the communications group working behind the scenes to make sure that data comes down and gets transmitted. And we're operating at about a 98-99% availability of our network systems on board through the NASA systems, which is an unbelievably high amount of data that they pass every day. And it's amazing what they do. But that's extremely important to us from an overall standpoint. It's also important from the science side. You don't often think about it, but we have some satellites that measure the moisture in clouds. It actually uses the electromagnetic spectrum of the water molecules in the atmosphere. We actually passively look at that to determine where clouds are by looking at the electromagnetic spectrum coming back from those clouds. So that's another area that can get clobbered very easily with communication satellites that could dwarf all the essentially emitted frequencies from the clouds and moisture in the atmosphere. So we have several satellites that monitor moisture in the upper atmosphere, and it's important for us to protect that portion of the spectrum so they can still passively monitor what moisture is contained in the atmosphere, which is very important data to us. This is our picture of spectrum. It's a little more complicated than the L4, L2 picture you saw, but the same basic concept. We have a space network where we relay a lot of activities off of, for example, at Mars. Mars Observer relays a lot of information back to the Earth from all the rovers that sit on Mars, and we use those. We have the TDRS satellite network in geosynchronous orbit that relays a lot of information from our spacecraft from the space station to the ground. It's also being used now extensively for launches. We're now getting away from having ground monitoring of radio frequency stuff from launches, and we're using the TDRS satellite to do that. And then once the data gets to the ground, we use essentially a terrestrial network to pass all that data around to get it to the right users in the world. So obviously, just from an overall perspective, there's a lot of communication going on with lots of different spacecraft throughout the solar system. Again, we'll talk a little bit more about spectrum specifically. These are the various bands you may hear of. The UHF band, which sits down there in the upper left. That's used predominantly for our spacewalks when our crews are out in spacesuits on board space station, or when shuttle is flying. We use the UHF frequency. We also are using that now for the cargo resupply vehicles. You hear SpaceX and Orbital, which will be flying the space station. We're using that frequency, the UHF frequency, for communications between those arriving vehicles and the space station. And that wasn't necessarily an intended use, but it turned out we had all the antennas up and down the truss of the space station for the spacewalks when the crews were out in their spacesuits. and it was an easy frequency to go use for these satellites that could be coming in along the radius vector, along the velocity vector, in any direction that gave them very good access to space station. We then have the L-band, S-band, which is a lot of communications that occurs in the S-band. And then we get to the higher X-band, which is a lot of deep space activities, planetary missions. Ku-band is used a lot for shuttle. We bring down high definition TV from space station using the Ku-band. And then Ka is kind of the new emerging frequency that we use a little bit also on space station and some other spacecraft. But again, this kind of just shows the overall range of spectrum that is used by the various satellites. So it looks pretty extensive when you look at it in terms of megahertz, from 30 megahertz, 300 megahertz, all the way up to 30 gigahertz. But if you really look at that spectrum, there's becoming a lot of competition for the various frequencies in that spectrum. These are our satellites that we have in orbit today. And you can see there's quite a variety of satellites up there that we're communicating with that the communications team keeps track of, and they all have unique frequencies. A lot of them are S-band and X-band, and we need to keep good spectrum spread between those to avoid interference. Let's talk a little bit now about how we manage spectrum. It has a domestic component. Each individual country takes care of their own activities. There's also an international component where it quickly bleeds over to the international community. We need to create some rules for governing what frequencies are used, and then we have to go figure out a way to go implement those rules. And I'll talk to you a little bit now about how that's actually done, which is pretty amazing. This is how it's really managed internationally. Under the United Nations, there's the ITU, the Telecommunications Union, and that actually relates back to, in the U.S. side, to the Department of State. So, and then that goes down to NASA, and then the non-government commercial providers. So in the little lower left-hand corner, the way it works is when we're going to, say, an ITU meeting or to the World Radio Conference where we start trying to allocate spectrum, it begins, at least on the U.S. side, with NASA, first of all, kind of working with the commercial sector to try to figure out which areas of frequency we want to protect, which is of mutual interest to both the commercial side and to the NASA side. Then we get our position kind of integrated by the Department of State. So here's the Department of State actually mediates between the commercial groups, the folks that want to use spectrum for direct TV, they want to use it for maybe a new cell phone coverage, a satellite communication system, all those things. Those individual requirements between NASA and this commercial company gets negotiated by the Department of State to develop a U.S. or United States position on who ought to have what spectrum in those regions. So that's where that process begins. Then that goes to the ITU, where there'll be a treaty essentially established or a voluntary regulation put in place of what frequencies will be used for certain aspects, and those are set up. And what's interesting is it's not a mandatory enforcement, it's a voluntary enforcement. So when you come together in the ITU, you're allocating this whole spectrum that I showed earlier into little pieces for various applications, and they'd be commercial, they could be international, they could be NASA's use, etc. And they all are then written down into a large volume of documentation. But those regulations, because the agency can't really talk in a legalistic standpoint, this is an absolute requirement, these are seen as voluntary. So then just to avoid communications problems and interference, everybody generally adheres to these rules. And then you have to go back to your individual government to go back and actually then put laws in place to keep the frequency allocated into various bands. So the purpose of this is to just give you some idea of how complex this activity is. These conferences occur every several years, and the preparations start at least almost from the last conference to the next conference. It's almost continuous meetings leading up all the way until the WRC, which will occur next year in January in Geneva, where we'll take the next set of issues. So all the issues have already been defined about a year ago, They've done a preliminary meeting already this year in January to set up the basic negotiation positions, and then they'll go into probably about a 3-week, 4-week actual World Radio Conference where all that stuff will finally get negotiated into the final set of regulations that come forward. And for me, it was the most amazing thing I've ever seen. I used to think space station was complicated, with 16 nations participating. When I went to the World Radio Conference, it was the most amazing thing I've ever seen. Here's a small country in Africa negotiating with the U.S. about a small piece of spectrum, and the negotiations were unbelievably intense. They were debating what the exact wording was in the voluntary regulation. It took almost 4 days to nail out, or to finally get agreement on what those regulations would read. So for me to see all that happen and then realize that that was protecting, in this case, it was protecting for this moisture measurement on the passive band, but for us to have to go work that hard to make sure that that band got protected was just an amazing activity that occurred over probably about a 2.5-year period. So then a little more of how the details work. The countries are kind of broken up into regions, and the United States is in Region 2. So as I described to you before, Department of State will go represent Region 2. Then you kind of build a political consensus within your own region, within Region 2, Region 1, Region 3, and then the European region, Region 1. And then each individual group then kind of gets together and starts working. So you kind of build up consensus before you get into the big meeting of who your partners are. So, for example, North America and South America, we'll get general agreement on what we want to carry as the major issues going into the radio conference. We'll have those negotiated up front. We'll have our positions up front. So then we go in as a kind of a group. Region 2 will generally have certain objectives they want to accomplish. The other regions will as well, and then they start negotiating until finally it gets to the final overall resolution that comes out of the World Radio Conference at the end. And this again is what I described to you a little bit before. These are the preparatory meetings that occur that lead up to the radio conference. The regional areas all come together, and then eventually comes out of the World Radio Conference a report that actually sets up and defines spectrum for use for folks. So again, I'll give you a little bit of things that are happening here. Explosive growth on the consumer wireless broadband has really accelerated the requirements of the wireless industry for spectrum. We heard it today earlier, right, when the BlackBerry was interfering with the speaker system here. That's a pretty common thing. But there are really no empty bands on this spectrum below 3 gigahertz, and it's getting to be extremely busy and extremely packed area. Industry has advocated for a new capability. They want some new ways of communicating. The general folks really want to use a lot of bandwidth. The applications, the iPhone, iPad, to be able to download pictures. A lot of folks, and there's a lot of interest. The new 4G activity is really picking up in that area. But the problem is there's just not enough spectrum in that region to make things go work correctly. So we're trying to figure out how to provide this spectrum to all the users, the broad community that wants it, but yet not interfere with the folks that are there already in that band. And this is a thing you may have read about in the papers, or at least heard on the news. This band of 1559 on up is that to 1557 in the center there. That's the GPS band. So the global positioning system sits right in that region. So all your GPS that you use in your car, the precision navigation, all those things sits in that basic frequency spectrum. And the blue line shows the sensitivity of those receivers. So they don't just receive right in that direct band. There's some spread about that band, and then there's a cutoff in that region. And what's happened is a new 4G LTE users come online terrestrially in the U.S. They want to put a 4G system in, and they want to use essentially the 2 bands. You see down there is the red bars down at the bottom. And it turns out that if they use both of those bands, it would actually clobber all GPS users. So it turns out GPS is becoming extremely useful in a lot of areas. It's now used in aircraft navigation. It's used in the next gen for aircraft separation. And this potential broadband user could come in and essentially wipe out all those applications. It's also now used extensively in the U.S. for farmers when they do pesticide application and they do fertilizer application on their fields. They actually use GPS on their tractors to actually precisely locate where they're putting down pesticides and where they're putting down chemicals. It improves their efficiency tremendously. And again, this terrestrial user for the wireless system would actually take all that capability away. But we've also figured out a very clever way of using GPS to monitor the way the atmosphere heats up and cools down. It turns out that the GPS frequency is so precise you can actually see the frequency shift as it travels through a denser air on the way to the ground. This was not intended for GPS, but our engineers got clever and figured out a way to monitor extremely small shifts in frequency. They could use that to determine the density of the air all the way down, which can be important to determining weather conditions. That was not an intended use of GPS, but an innovative solution that some folks came up with. That also gets really clobbered by this new user that's coming online. So in the U.S., we're having a huge debate about how we accommodate the desire to get wireless to everybody, to all our users. At the same time, we protect the GPS band that sits out there. And it's a very interesting debate from my perspective. What I see as interesting is the broadband user. They're saying that GPS is too sensitive, and then the GPS group out there says that you're interfering with my space, you shouldn't be that close to my frequency. And you can see that they're actually not impinging directly on the frequency, they're actually off the frequency, but it spills over into the GPS. So the broadband community essentially is saying that the GPS receivers are too sensitive. If you would put all the right filtration in there up front, we'd be allowed to go use your broadband. So you, GPS users, should pay to retrofit every GPS receiver that sits out there with new filters in place. And then the GPS community says we can't afford to go do that. It'll cost millions and billions of dollars to retrofit every GPS receiver we have. So you need to stay out of our spectrum and go find another location to go use. The broadband user said, I negotiated for these two spots with the Federal Communications System. I have approval for that. I have a license. So we're going to have to go off and work that. So this is a huge debate going on now. I think what's going to happen is you're going to see the terrestrial user go use potentially that lower left-hand band up there, the little red bar. We think we can maybe work with that. It may still take out some precision users, but we're doing some testing there, and we may just allocate them to just the one band on the left. But then the question is, will that provide enough bandwidth for them to actually do their applications? If you look at the technical desire, they really need both of these bands to meet the user requirements in terms of the amount of data they want to transfer. So it'll be interesting to see if they get limited to just that one band, or they can go negotiate with somebody else to find another band. But the purpose of all this discussion is to show you how I started from this big political process that's actually the UN, State Department, all that, to now a real world problem which actually affects you, how you get information to your device, and which one do you want? Do you want your GPS to work, or do you want your cell phone or your BlackBerry or your iPad to work? So you get to choose. And the UN will decide for you. So again, this is some things that you ought to think about as you talk about this. This is an extremely interesting and dynamic period. And I think that these last two things are some questions I want you to think about and maybe talk in some of your groups offline. Is, how are the current regulatory structures and processes for managing the use of spectrum today fit with the rapidly changing technology and increasing requirements? Is this UN semi-bureaucratic process that was developed way back when, right? Essentially when Marconi built the radio, and it worked well then. How does that fit today with today's evolving technology where users are getting unbelievably creative and they're figuring out new ways to use GPS to actually measure the density of the atmosphere? That was never envisioned, right? You now use GPS all the time in your cars and where you get around. You have it on your devices to go find it. This is a totally different use of spectrum. It's much more critical to us than it ever was before. And are those processes we have in place, are those the right processes to actually manage such a critical resource? And then the other question I think you ought to think about is, does this framework that I just showed you a little bit about on the previous page, does it foster technology innovation, or is it actually holding us back? Is it keeping that entrepreneur away from figuring out creative uses for GPS, or a new way to go to the 4G network to actually get more data to your handheld device. You know, does this framework, is it responsive enough and fast enough to actually support the innovation that can come out of this new system? So again, spectrum seems like an archaic thing. It's the electromagnetic spectrum, but it really impacts us every day. And these things, these questions are things that I think you ought to think about, because if we don't address these up front, pretty soon we'll end up in a situation where devices don't work, they interfere with each other, and that's not going to be acceptable. So anyway, hopefully I gave you something to think about that's a little different than actual spacecraft and exploration. I can talk about those things too, but this is kind of the backbone and behind the scenes of things that go on every day that actually make all these spacecraft and allow us to communicate with them and send commands to them every day. So thanks for your attention.